So in this segment, we will be answering a question from the past paper 2015, question 2BI, where we asked to calculate the plastic moment capacity. Plastic moment capacity is simply the moment which is exhibited by the beam just before a hinge forms in a beam. And to calculate this, you have two options. So one option is by calculating using first principle. Now, if you do it by first principle, this allows you to calculate it for if you understand that method, you can do it for beams which have weird cross sections, so unusual cross sections. However, you can use the formula, but this is simply limited to the shape of the beam. So common shapes in the beam, such as squares, circles, I-beams, and such. And I will show you the equations of those and how to use those equations later on. But first, we'll begin by using the first principle approach. Now, what you must do with this approach is you identify the neutral axis of the beam. So in this case, it's in the middle of the beam, and it's symmetrical the shape is symmetrical from the neutral axis. So therefore, we only need to consider the top half of the neutral axis, as you can see in this new diagram, and we simply have to just multiply by 2 afterwards to account for the second part that's below the neutral axis. So as you can see, I further divided the shape into two colors. Now the green color, the reason why it's green is simply because both of the two shapes are the same, and what you do is you work out the area of each of these segments, and you multiply it by the distance from the centroid to the neutral axis. So let's begin. So you have MP, which is the plastic modulus. It's going to be equal to 2, which is simply taking account of the bottom half of the shape, or bottom half of below the neutral axis, times by 355, which is the yield stress, times by. So now we're going to do each of these sections. So let's go in the green section first. So the area of that is simply going to be 50 times by 10 times by the centroid distance. So here the centroid is obviously going to be half of 50 millimeters, which is 25. And now, since we have two identical shapes which will have the same area and the same distance from the centroid to the neutral axis, we can times it by 2 to account for both of them. And now let's go for the red segment. So the red segment is simply going to be 18 times by 10 millimeters times by the centroid distance, the distance from the centroid to the neutral axis, and that's going to be 40 millimeters plus half of 10 millimeters, which is 45 millimeters. And yep, so once you plug that into the calculator, you will get a value of 4331000 newtons per millimeter. Yep. Okay. Now you can use the formula approach. So the formula for a square, so this is the second method. Actually, might denote that simply using so the second method. So we use the formula, we use MP is equal to BH squared over 4 times by the yield stress. Now, in general, this is simply going to be equal to ZY which is the modulus, plastic modulus, and times by the yield stress. So this is just a general equation for NP, and it could be denoted with these symbols. Now let's look at now since we have a hollow section, this is going to be the outer section minus the inner section to get the value, the plastic modulus of the entire section. So as you can see, the outer section is going to be, since it uses the formula BH squared over 4, it's going to be 100 times by 100 squared divided by 4 minus the inner section, which is 80 millimeters times by 80 millimeters squared divided by 4. So I'll write that down, and if you write that down, and we have to times that by yield stress, which is 355, and this also gives you the value calculated using first principle. Now, where it's best to change this into kilonewtons per meters, because the beam above is in meters, so to make the units match in the later part of the question, we're going to make it to kilonewtons meter, which makes it equal to 43.31 kilonewtons meter. That ends this segment of the video. We'll tackle part II in the next segment.